Let's look at a theoretical result from section 3 and analyze it a bit more closely. The result is this. Let F with components P and Q be a C1 vector field on an open and simply connected region D. Further, suppose that the partial of the first component P with respect to Y is equal to the partial of Q, the second component, with respect to X throughout the region D. The conclusion is that F is then a conservative vector field. All right, so F being a C1 vector field simply means that the first partials of P and Q exist and are continuous, okay, which makes sense as a reasonable condition. But what I really want to consider is this notion that condition of simply connected comes into play. It seems to come out of nowhere. It's a geometric condition about D. So remember that if I have a region D, let's look at a couple examples. So if I just have this filled in solid region, whereas on the right hand side, if there's a hole in the region, then this is simply connected and this is not simply connected. And essentially the problem with the region over here is exactly this hole in this region in the plane. Okay, so a region being simply connected is really a geometric, in fact a topological condition about the region, and it's interesting that this sort of appears out of nowhere when we're just studying this calculus. And what I want to demonstrate is that if I remove the simply connected condition from my domain D, so if I look at vector fields defined on regions like this, then this theorem will fail to hold in general. And so I should be able to come up with a counterexample. So I should be able to find a specific vector field F that satisfies this condition as partial derivatives behave the way they should, but that it's not conservative. Now, how do we show that a vector field is not conservative? Well, we're going to take advantage of this result about conservative vector fields. So if F is a conservative vector field and C is any closed curve, then the integral of f dot dr over C is going to be 0. Now, this proposition falls straight away from the fundamental theorem of calculus. So suppose C is this. So here's C, it's this closed curve, and say it starts and ends at this point P. Now it doesn't really matter which point we pick, but let's just label one specific point on the curve as P. Then the integral over C of f dot dr is the same thing as, well, if f is conservative, that means that f equals the gradient of some potential function, little f. And so we can replace cap f with the gradient of little f. And the fundamental theorem of calculus says that this is just equal to little f evaluated at the endpoints. And so that's f of p minus f of p. All right, and because it starts in at the same point, C is a closed curve, then that's what guarantees that we'll get 0 for this result. Okay, so this proposition is a straightforward consequence of the fundamental theorem of calculus for line integrals. So what we want to do, so this is where, if we're going to look where D is not simply connected. And what we want to do is we want to find a vector field F and a curve C inside the domain where for the vector field we have p sub y equals q sub x, so we have this condition holds, but we want to find a curve where the integral of f dot dr is not equal to 0. All right, so if we find this f such that this condition holds but this condition here doesn't hold, this integral is non-zero, then that would be a counterexample to this theorem in the case where D is not simply connected. So this theorem does hold in general if D is simply connected, so for regions like this. So we're going to find a counterexample in the case where D is not simply connected. So the next thing to do is to actually find a specific F and C and D where this actually works, and that's what we're going to do on the next slide. So here we have a very specific vector field f on a very specific domain D, and we're going to look at this curve, which is in fact the unit circle, which is inside this domain D. And what we want to verify is that this is a specific counterexample to the theorem that we have just looked at in the case where D is not simply connected. So we're going to verify that dp dy is equal to dq dx for our vector field f everywhere on D, but that the integral of f dot dr over our specific curve C is actually non-zero. And that shows that f is actually not conservative on D. All right, so let's think about the specifics a little bit more closely. So our vector field f is negative y comma x, and then both components divided by x squared plus y squared. So it's not defined exactly at the origin where x squared plus y squared equals 0, but it's defined for all of R2 other than the origin. So in fact, we're missing a point right here at the origin, and so we can think of this as an infinitesimal hole inside the region D, and so in fact D is not simply connected. Okay, so we're not finding a counterexample to the theorem, we're finding a counterexample to the theorem if we look at non-simply connected regions D. All right, now some arrows for this, some vectors for this vector field are shown here, and the minus y comma x, that's what gives you this sort of rotation here. So every vector is perpendicular to the vector that gives the point xy. And then the x squared plus y squared makes the length of the arrows decrease as I move away from the origin and increase as I move closer to the origin. So the closer we get, the longer these arrows would be. They'd be getting very, very long as I got close to the origin. And on the other hand, as I move away from the origin, they get much smaller. Okay, so let's first verify these partial derivatives. So we have the partial derivative of this with respect to x. So dq dx is equal to, and now we have a little bit of a quotient rule work here. So we have the bottom x squared plus y squared times the derivative of the top with respect to x, which is just 1, and then minus the top times the derivative of the bottom with respect to x, which is 2x, and then all of that over the bottom squared, x squared plus y squared, quantity squared. And so what we get is we get x squared plus y squared minus 2x squared. So we get y squared minus x squared over this denominator, x squared plus y squared squared. All right, so now let's calculate dp dy. So we're taking the partial of this function with respect to y, and again we get bottom times the derivative of the top with respect to y, which is negative 1, and then minus, and then top, so a minus y gives me a plus y times the derivative of the bottom, which is 2y, over x squared plus y squared squared. So this is times negative 1. So here I get negative x squared minus y squared, and then plus 2y squared is actually positive y squared minus x squared, divided by x squared plus y squared squared. And so we can see these two are equal. We just sort of brute force verified it. So we've shown that dp dy is equal to dq dx. All right, so f does satisfy the condition of the theorem that the partial derivatives behave well. And so now at the same time we want to show that this integral of f dot dr over this closed curve C is in fact non-zero. Okay, so we can think about, so t equals 0, so we have the unit circle right here, and the curve C goes around. It's not a perfect picture, but we get the unit circle traveling around here. Okay, starting at 0 and ending at 2 pi. So let's just go through and compute this. So we need r prime of t, which is negative sine t cosine t. And then we also need f of r of t. So we're going to plug in, oh, there should be a comma here. So this is cosine t comma sine t. So we're going to plug in x equals cosine t and y equals sine t. Well, in that case, x squared plus y squared is equal to 1. So both these denominators are just 1, so we can ignore them. And so we get minus y, so we get minus sine t, and then x, which is cosine t. All right, so the integral over c of f dot dr is equal to the integral from 0 to 2 pi of f of r of t dot r prime of t dt. So we get minus sine t times minus sine t plus cosine t times cosine t dt. And so we get a sine squared plus cosine squared. So in the end, this simplifies to just the integral of 1 dt, which is equal to 2 pi. So it really wasn't very hard with this parameterization and this vector field to show that the integral of f dot dr was equal to 2 pi. More importantly, it's not equal to 0. And so this verifies that we have a counterexample. If d is not simply connected, we found a vector field and a curve for d such that the partial derivatives sort of behave the way they should, but at the same time, the fact that this integral is non-zero implies that f is not conservative in our region D. Okay, so that means that we actually do have a counterexample, and we're allowed to find this counterexample exactly because the region D is not simply connected. So in the end, we conclude that this sort of interesting geometric topological condition that our regions must be simply connected is necessary to include in the theorem for it to hold true for all vector fields and all regions.